Hi guys, so here we're going to bring together everything you learned about from Section 4 into electrochemical cells. So you'll need your notes for this. We're going to talk about what the different types of electrochemical cells are. So here they are. We have an electrolytic versus a voltaic or a galvanic. We've seen electrolytic, so this is when I had you at the beginning of the school year coat a nickel coin with copper. So I made you essentially turn it to copper. So we've done that before. I'm just kind of reminding you of what we did, because it's been a while. And we're now going to introduce what voltaic or galvanic cells are. So we'll do voltaic or galvanic cells first. This is what is operating inside of a battery. So this is what really makes your batteries run, or how they're powered. These are going to be spontaneous reactions, meaning that you don't need an outside power source. In fact, they are a power source just by doing this. So again, they are spontaneous. And you have your anode versus your cathode. And you've seen this before when it came to cell potential. So on the left-hand side here, you have your anode. In this case, it's zinc. Your cathode on the right-hand side is going to be copper. And these are each individual half cells that are occurring in here. Right? So what ends up happening is that here in your anode, you have a piece of zinc. It's in a solution of zinc nitrate. So what ends up happening is oxidation. That solid zinc ends up becoming a zinc ion plus some electrodes. So this is why, again, it's at the anode, because it's undergoing oxidation. Remember, unox? So here's the particle diagram on the left-hand side. So you see all of these little circles. They each represent a zinc. What ends up happening is that these zincs are, when you see them in the metal, they're solid, right? So they're going to be a neutral charge. They end up actually giving away those electrons and becoming zinc ions in solution. So really what ends up happening is that you're going to wear away part of this zinc electrode if you keep letting it run. And so yeah, they'll end up becoming zinc ions in solution. So they'll kind of wither away. So the mass of the zinc electrode will decrease in this anode. So electrons are flowing from the anode to the cathode. You can actually see that, hey, look, a little light bulb is running here. By the way, I've tried to get a light bulb to work in lab. It doesn't. Again, I'm going to try. Hopefully it does work for you guys eventually. Again, those electrons are flowing towards the cathode. In this case, it's going to be copper. So it's undergoing reduction. Those copper ions are going to gain some electrons and become copper solid. So here's how it works. Take a look at the particle diagram on the right-hand side. So you have this copper electrode in a solution of copper 2 nitrate. So those copper ions, those copper plus 2 ions, are going to gain some electrons from that electron flow and then attach itself to the copper electrode. So here on the cathode, it's going to gain more mass because it's taking all those ions from the solution and making them neutral atoms as a solid. One thing here is something called the salt bridge. So the salt bridge is super important. It actually lets this reaction continue to occur. So this is a glass tube. It has little plugs on the end. It's kind of like a porous plug, kind of like as if you had cotton in there. And it's filled with a solution of KNO3. So the positive potassium ions are going to go towards this cathode. So it's going, again, towards the cathode, towards the copper 2 nitrate solution, excuse me. And those nitrate ions are going to go towards that zinc, towards that anode. The biggest thing here, the salt bridge, is for a flow of ions. The wire is for a flow of electrons. There's a lot going on in here, so we're going to summarize it right here. Here are your major key points. I've seen these questions on the regions, so you need to know each and every one of these key points. First, these voltaic or galvanic cells are going to be spontaneous, no batteries required. Electrons will flow from the anode to the cathode through that wire. The cathode is where reduction occurs. The mass will increase because those ions are becoming atoms in solution. You need to remember all of this. Again, this is a key free response. The mass increases because ions are becoming atoms. And the cathode is positively charged. The cathode is positively charged. The anode here, again, undergoes oxidation, unox. Remember that? Unox. Oop, there we go. Reduction cathode. Here, the mass will decrease. This was our zinc. The mass decreased because those atoms became ions in solution. And that anode will be negatively charged. You'll need a salt bridge. That salt bridge is for a flow of ions. And this is what occurs inside of a battery. So again, it's spontaneous. It occurs on its own. It does this because the standard reduction potential is going to be positive. And we did this when we talked about standard reduction potentials, when we had the reduction potential table, we did cathode minus anode, and we looked at copper and zinc. It ended up being 1.10 volts. So I'll kind of go, well, the 1.10 volts were kind of what helped in that case, in the case of this picture, let that light bulb light. All right, so this again is a spontaneous reaction. A non-spontaneous reaction, we've already seen this and we've had to make this non-spontaneous, is an electrolytic cell. We've done this with electroplating. So this is when you took our nickel coin and put that in a solution of copper sulfate, and that copper sulfate is going to be less active than that nickel, so it's not going to do anything. Instead, we have to attach a battery to it in order for it to actually work. Here, this is a picture actually straight from one of the reagents. You see the power source. So this is going to be your battery. And sketch this picture into your notes as well. You have one beaker. So the battery, let's see, whatever you want to plate. So we plated the coin. In this case, they're going to plate a key. That's attached to the negative end of the battery. The positive end was another little electrode. So let's kind of empty some of this out. So again, we want to make sure that that negative part is going to be whatever we want to plate, because those positive silver ions in solution will attach onto that negative nickel coin to go ahead and plate it. So really, taking some nickel and plating it with some silver. We do this with costume jewelry as well. We take some inexpensive jewelry as the core and then plate it with gold or silver to make it look more expensive. The bumpers of your car, we plate that with chrome. It's just on a much bigger scale and not in a tiny, teeny beaker. But again, with this does happen. This is what we do all the time just to make sure that we prevent corrosion of any metals, as well as just to kind of make it look nicer. It's more of an aesthetic thing, really, for a lot of metals. Anyway, so here, we want to kind of label what everything is. So normally we think of the cathode as being positive. In the electrolytic cell, the cathode is actually going to be the negative part. So this is your cathode, this part's your anode. So your cathode is that coin. And that cathode is going to gain mass. It's going to have those silver ions become silver atoms plated onto that coin. A battery source is needed because this is a non-spontaneous reaction. So let's look at the key points for electrolytic cells. Again, it's non-spontaneous. Oh, by the way, anything in red in here is going to be how it's different from the voltaic or galvanic cell. Right? So it's non-spontaneous. Electrons still flow from the anode to the cathode through the wire. In the cathode, it still undergoes reduction. The mass still increases because ions become atoms. But this time it has a negative charge. So that's how it's different from a voltaic cell. The anode still undergoes oxidation. The mass still decreases because the atoms are becoming ions in solution. This is instead going to be a positive charge. Here the salt bridge is not needed. There's no salt bridge at all, but it does need a battery for it to actually occur because that electrocell potential is probably going to be negative. It's a non-spontaneous reaction. And usually you'll see it in a beaker with one picture. Another thing you'll see here is when you take, if you're trying to decompose water into hydrogen gas and oxygen gas. So that's going to be an example of an electrolytic process. All right, so for those of you who like tables like me, this will kind of help you understand a little bit more of it. So in the first column I have, actually the first main column, I have just rows for headings. Then I have the electrolytic cell. That's what we did way back at the beginning of the year, coated some nickel, or coated a nickel coin with copper. And then on the right-hand side, we have the voltaic cell, which we just introduced today. So we'll take a look at each of these things. So spontaneity, does it need is it going to occur on its own, or is it going to be non-spontaneous? So an electrolytic cell is going to be non-spontaneous. All right, there we go. Versus a voltaic organic cell is going to be spontaneous. It does not need a battery to occur. In fact, that's our next question. Does it need an outside power source? Yes. Battery needed. Alright, and again, it's kind of scrabble, but that says battery needed. For voltaic or galvanic cells, no battery needed. In fact, it is, a battery. The energy transfer. Oh, this was big. I forgot to mention this before, so make sure that you get this. In the electrolytic cell, you have electrical energy converted to chemical energy. Remind me to remind everyone in class about this too. So again, electrolytic cell, you have electrical energy, so this was what was inside of the battery, becoming chemical energy. A voltaic or galvanic cell has chemical energy converted over to electrical energy. Again, huge key point here. The next thing, salt bridge needed. No salt bridge needed for electrolytic, but yes, it is needed for a voltaic or galvanic cell. The number of beakers for electrolytic, it can be just one. Sometimes you'll see two. That's okay. But it can just occur in one beaker. Voltaic or galvanic usually has two. I don't know what they'll throw at you, but I've always seen two. The charge on the cathode for, we'll do voltaic versus and galvanic. These are normal. So what we normally think, cathode is positive, anode is negative. It's the opposite for electrolytic. So the cathode is going to be negative for an electrolytic and positive anode on the electrolytic. Oxidation still occurs at the anode on both of them. Reduction occurs at the cathode on both of them. All right. Electrons flow still from the anode to the cathode. So you have electron flow essentially from the anode to the cathode. I don't know if that helps you at all. Random miscellaneous stuff. This is electroplating, or this is also breaking down water to hydrogen gas and oxygen gas. That's not balanced. I feel like I need to balance it there and there. Good. These are both going to be gases as well. All right, so if you think about hydrogen fuel cells or hydrogen-fueled cars, that's actually what's occurring inside of them. And voltaic or galvanic, this is a battery. So it is a battery. All right, so those are just some key points. Again, remember those key points from before. And do me a favor, get the fact that electrolytic is an electrical to chemical conversion, energy conversion inside of those key points. And this part too, chemical to electrical for voltaic or galvanic. All right, to some, pretty much that was our summary of voltaic versus electrolytic cells. So let me know if you have any questions. Unfortunately, this is a lot of memorization, and a lot of practice as well. So we can definitely do a lot of practice in class. Have a great day, guys.